All right, folks, Bass Action is back in action here. We're going to actually look at some examples here where we're going to apply our transformations to our library of functions. Now, these first two examples are going to look at our greatest integer function and combine that with our transformations of horizontal stretches and compressions and our vertical stretches and compressions. Now, on our first one that we have here, what I want you to first notice and just think about what we're expecting in the behavior. We can see that this function is a greatest integer function that has a horizontal stretch or compression, and what we want to think to ourselves is the fact that this can be written as a 1/3 x, which means that it's moving at 1/3 the pace, meaning it's going to take 3 times as long to complete its cycle. So what we would normally have on a step function is a short step and a short step and a short step. But since it's moving at 1/3 the pace, what we expect to happen is instead of a step only being this long, we're going to expect the step to be 3 times as long. Now, on a greatest integer function, it might be easier if we draw out just a small t-chart for ourselves here. So just so that we understand what's actually happening here. So if I pick some values, for example, I can pick a 0, I can pick a 0.5, and I can pick a 1, and let's just see what happens when we evaluate. So if I put a 0 into my function, I'm actually finding the greatest integer of 0/3, or in other words, the greatest integer of 0. That, of course, is just going to be 0. Now, when I do the greatest integer of 0.5/3, okay, I can think of that as 1/2 times 1/3. That's definitely not to the next whole number, so I'm going to stay at my 0. And even when I have a 1 here, I have the greatest integer of 1/3. That's still not to a whole number, so I'm still at 0. So I can see that even at 1, I'm still not moving up. And in fact, it's not until I get to a 3 and I do my greatest integer of 3/3, in other words, my greatest integer of 1, and now I'm finally going to jump to the next level. So when I graph this, just as we expected from understanding our transformations, I expect this first step to be very long. It's not until it gets to 3 that we actually jump up to our next step. So now we understand how long our steps are. We could, of course, extend our t-chart if we wanted. I like to work on the positive side to create my steps, and then once I have that understanding, I can just make that behavior happen on my negatives. I think that's an easier way to understand our greatest integers. So let's look at what happens on our next one. And just like we saw on that previous page, my computer program didn't want to create these double brackets for me. I don't know why it didn't want to transfer that, but this is just our other notation for greatest integer. So when I'm creating this t-chart, what I'm expecting this to happen is it's going to stretch my steps. So it's going to stretch my steps vertically. So instead of them only being spaced apart by 1, I expect a much bigger leap. So I expect to go from here all the way up to here. But the length of the step is going to stay the same. So let's just pick some values again. So I'm going to pick my 0. And I'm just going to use my integers this time and see what happens with those. So if I put a 0 into my function, my greatest integer function, I actually get still 0. And the function that I'm given, I can see here, wants me to take that value and multiply it by 3. That, of course, is going to keep me at 0. But when I put my 1 into my greatest integer function, that puts me at a 1, but what I'm given wants me to multiply that, so that gets me at a 3. So I can see that my steps are going to be bigger. So I know that I'm going to start off at 0, and I can see from my t-chart that I'm going to jump when I get to the integer of 1, but I'm going to jump a much bigger jump this time, and I'm going to jump all the way up to 3. Now I would expect it too that I'm going to make a similar leap, and sure enough, the greatest integer of 2 is 2, but I need to multiply that by 3, which makes me jump all the way up to a 6. And just like I did on the previous example, I can just reflect the same behavior in the negative direction. So I would have my open circle here, and the length of my step would remain the same. Integer functions definitely require some thought. Now let's take a look at a piecewise function. And you should have seen these before, but these often cause students some trouble. So when we have a piecewise function, what we're going to do is we're going to graph each piece individually. So I have a function, and then I have a specific domain I'm going to keep, and a function, and a specific domain I'm going to keep. So the first thing I'm going to do is I'm going to work with that square root function. Now, I should be able to recognize that this square root function has a horizontal shift because I can see something's been added or subtracted, and I have a reflection. What might be helpful is to make a small t-chart here. So when I make my t-chart, what I'm going to do is I'm going to take this 5 minus x, my radicand, and I want to set that equal to values that I know are easy to work with my root. So I know that when I work with my t-chart, what I ultimately want to be able to do, thinking left and right hand side here, is I would like to be able to evaluate the square root of 0. So what I want to do is I want to know what value of x would make 5 minus x equal 0. Well, that value of x would be 5. So if I put a 5 into the function, then I could evaluate square root of 0, which would give me 0. Now, continuing that process, I would like to be able to do the square root of 1, the square root of 4, and the square root of 9. This is what we call a smart t-chart. So we're going to think about what we want to be able to do on the right-hand side, and then we'll go back and we'll figure out what x values will make that easy for us. So I need my 5 minus my x to equal 1. In other words, I want to solve the algebra, and I'm going to use an x value of 4. I need my 5 minus x to equal 4, and that means that I'm going to choose an x value of 1. And my 5 minus x equal 9, which means I'm going to choose my x value of a negative 4. So now, if you're not quite sure how those are truly going to work for us, we can think through that process. So if I put a 5 into my function, I can see that 5 minus 0 is 0. If I put a 4 into my function, I'm going to have a 5 minus 4, or a 1. In other words, I get a nice square root of 1. When I put a 1 into my function, I get a 4, so now I get 2. And when I put a negative 4 into my function, I have 5 minus the negative 4, or 9, and I get 3. So the ordered pairs I'm working with are 5, 0, 4, 1, 1, 2, and negative 4, 3. Those are the points I'm going to graph. Now, I like to graph the entire function first. So I'm going to do 5, 0. I'm going to do 4, 1. I'm going to do 1, 2. And I'm going to do a negative 4, 3. And I'm going to graph this entire function to start with. So that's my whole square root function. Now I'm going to go back and I'm going to look at the fact that I actually only want to keep where this function is, its domain is less than 1. So I'm actually going to erase. So I'm going to first find x value of 1. And I only want to keep the portion of this graph for x values of 1. In other words, I am going to erase, again, I'm going to find this 1, and I'm going to erase everywhere that the x values aren't 1. So this whole part of the graph is going to disappear. And right here at x equals 1, I'm going to turn that into an open circle. Because on my domain, it was supposed to be open. So that's the only portion of my square root function I'm going to keep. Now I'm going to use a new color for my next part. I'm going to graph a line. This is simply a line. My next piece is a line with a y-intercept of 3 and a slope of a -2. So I'm going to go down to an over 1 and down to an over 1. So when I graph this line, again, I'm going to graph this entire line, and then I'm going to come up here and I'm going to look at this domain. And I only want the part of this line that is between x values of 1 and 4, which means I need to erase. So where my x value is 4, everything to the right of that needs to go away. And at my x value of 1, everything to the left of that needs to go away. Now I can go back and I can fill in some points here. It's specifically at x equals 1, it wants to give me a solid dot. So at x equals 1, that means that I have the point 3 minus 2 or 1. So I have the point 1, 1. And at x equals 4, I'm going to do 3 minus 8, where I have -5, and I'm going to give myself an open circle there. So what you can see here is that we have a slight little gap between our two pieces of our function. And that's going to be important for us when we answer our questions over here to the right. So my domain, I can see, is from -infinity. As I follow along, it's from -infinity. At x equals 1, it still is included, but it's part of the y. And then my domain stops at this 4. So I'm going to go to 4, and those are both going to be open. My range, I can read it from my graph, is going to be a -5, open, and then it's going to continue up to my y value of a 1. It's going to restart at a y value of 2, and it's going to continue to positive infinity. Now, is this graph continuous? All we're doing here is we're tracing the graph, and if I have to pick up my pen to move from the blue piece to the red piece, which I did, we say that the graph is not continuous, so no. Where's the graph increasing? As I move from left to right, this graph is not increasing anywhere. So we're going to say none. Where is it decreasing? It's decreasing on its entire domain. So we can actually repeat our domain here. So it is decreasing on the entire domain. -infinity to, I'm actually going to write this as a -infinity to a 1. And I'm not going to include that 1 in either point. And I'm going to restart it. Oops, didn't mean to write the infinity there. I meant to take that only to a 4. Now, why did I restart this at the 1? Because at 1, we moved from our two pieces of our graph, and we don't want to include it in either part because it's considered an endpoint. When we evaluate the function for a particular value, so for example, -3, what we do is we go and we look which part of our domain does it include it in. So is -3 less than 1? Yes, it is. So when I evaluate this, I am going to only put that -3 into the part with the square root. So x minus my -3. In other words, I'm going to have the square root of 8 that I could simplify to a 2 radical 2. Now for our x-intercepts, we are going to go ahead and take a look at our function and see what we get in either one. So we are going to actually set each function equal to 0. Some parts might get rejected. So I'm going to set each of my parts equal to 0 here. So I'm going to say the square root of 5 minus x equals 0. Square both sides. So I have 5 minus x equals 0. In other words, I have 5 equals x. Now, what I'm going to need to do is I'm going to need to go back and look at my graph because I've taken off parts of my graph. Do I actually have this point? Do I have the point 5, 0 actually on my graph? And the answer is no. Remember, we erased that part. So this does not count as one of my x-intercepts. So now I can go to the next one. I'm going to take 3 minus a 2x, and I'm going to set it equal to 0. So I get 3 equals 2x. I get x equals 3 halves. I can write that as an ordered pair. And I can go look at my graph. Is this point right here on my actual graph? And sure enough, that's still on the graph. It didn't get erased. So that becomes my x-intercept. For the y-intercept, all we have to do is let our x equal 0, so we simply just need to evaluate our function. So we're just going to let our x equal 0 like we always do. So let x equal 0, or in other words, find f of 0 like we did, like we found our f of 3. So f of 0 goes into our square root function because 0 is less than 1, so we have the square root of 5 minus 0, or in other words, the square root of 5. We can write that as an ordered pair, 0 square root of 5. That's all we've got.